Hello everyone, I'm Vaishnav and I'll be presenting the third project of Nand2Tetris today. So when we get introduced to the project, it focuses on sequential logic where the output depends upon the present inputs as well as the sequence of the past outputs. It's different from combinational logic where the output only depends on the present inputs. We'll also come across flip-flops, memory units, and counters. So here are the chips to build. If you have to build these chips, we need to have a good knowledge of the chips in projects 1 and 2, as well as the data flip-flop, which is a particular flip-flop which can store temporary data in digital systems. And from these elements, we build these 8 chips totally, out of which the first 7 can be treated as a family of sequential chips. And the last one, which is the program counter, it is a special chip which is used to keep track of the memory address of the next instruction to be executed. We'll see it in detail in the coming slides. So let me just describe about each chip, following which we'll go to the simulation. So the basic chips in this project will be the 1-bit register, which is known as the bit. And it is the simplest building piece, which represents a single bit of data. It has 2 inputs, in and load, and has a single bit output. The chip can load a new bit value based on the load input after storing a single bit of data. Next comes the 16-bit register, which has a 16-bit input and a load input as well. And the output is also 16-bit. The functionality is quite similar to the 1-bit register. Now we come to the next level where we see the random access memory unit with different memory locations. According to their names, we have RAM 8, which consists of 8 memory locations, 64 with 64 memory locations. That's for RAM 64, and RAM 512 has 512 memory locations. All three have 3 inputs common: in, load, and address. The in input specifies the value to be stored. The load determines whether to store the value of the specified address, and the address provides the location where the value should be stored or retrieved. Now we come to RAM 4K and RAM 16K, where the memory capacity is even higher. For RAM 4K would be 4096 memory locations, and for RAM 16K, there are 16,384 memory locations. And these chips follow a similar structure to the previous RAM chips that we saw. And finally, we come to the program counter, which is represented by the PC chip. It keeps track of the memory address of the next instruction to be executed in a computer system. It has 4 inputs totally. We have the basic 16-bit input, then the load, increment, as well as the reset. And the output is also 16-bit in this case. The PC chip updates its value based on these inputs, allowing the control of program execution flow. So that was a quick introduction to each chip that we are going to implement. So let's start the implementation in the hardware simulator. So here's a window as we've seen in the first 2 projects. So we'll start loading the chips. So if you can notice, this Nand2Tetris third project is being divided into 2 parts and in 2 folders, A and B. So the A folder contains these 5 chips, and the B contains these 3, which are the remaining 3. So let's start loading one by one. So let's start with the single bit register. we run the TST file, and it's a bit long, so we can make the compilation go faster. So you can see there are a lot of inputs and conditions out here, a lot of process to work on, and we can finally see the output for each case, for each amount of time. What are the values of the in, load, and out, as we have seen. And when we compare it, we get the same output here, which results in getting the successful output. Now let's uh, run the register, which is for the 16-bit. There's also a similar set of process, except we are seeing the 16-bit input right here. And let's observe the output very soon. The output is also represented as a 16-bit. This is the decimal form of the 16-bit. And we can compare and check that we got the same output. We'll follow the same procedure for RAM 8 and RAM 64 right now. And we can see the corresponding output for it. And let's go to RAM 64 now. And I'll view the output. And we have in, load, address, and out, as we see here, at different timestamps. And we'll move to the program counter now. And it has different inputs. As we've seen, we have in, reset, load, and increment. Yeah, so let's run it. So, and we'll view the corresponding output. So we have a different set of inputs and outputs, as we've seen. So we have finished checking all the chips in this folder. Now let's go to the other folder where we have the higher level RAM chips. So let's start with 512, 512.txt. Now this is the output for it. And the inputs are pretty similar to the previous RAM chips. And we get the corresponding values for it. And let's finish off with the 4K and 16K. Let's see how different it would be. its memory capacity being very high that it has a lot of addresses to store. And see, these are the corresponding output values for these combination of inputs. And see what happens in the 16K. So we have a different RAM 64 chips out here. It's a combination of all these. So let's roll it and run it. The output of it. When we check it with this, we get these combination of outputs for RAM 16K. And I'd also like to show when we have also seen that combination of RAM 64 is also used for the RAM 4K as well as RAM 512. So with this, we are done with exploring all these 8 chips for this project. These 8 chips are fundamental building blocks used in the Nand2Tetris course to construct a computer system which starts from basic logic gates and progressing towards a complete working computer. Each chip serves a specific purpose and contributes to the overall functionality of the system. So with that, I would like to end the session. I hope you found this enlightening, and I would like to spare some time to give my sincere thanks to Abdul Qadir sir for giving me this wonderful opportunity to explore the software and present all these 3 projects which I've done. And it was indeed a wonderful journey for me to explore different ideas in the field of computer architecture as well as digital systems. I learned a lot through the software, and I'd also like to thank every one of you who are watching this video. And with that, I'd like to end. Thank you very much.